Okay, uh, we were talking about the discharging phase of our piezo injector. Okay, I just reported in this whiteboard the section of the voltage across the piezo injectors and the current through it that is related to the phase through which I discharge the capacitor CP. As you can see in this plot here, okay, there is the phase in which the voltage is reduced in order to, let's say, have a deformation which is made to get the rest position of our piezo injector, so closing the injector, not having the injection of the fuel into the combustion chamber. In this phase, the current IP here is, say, negative. Okay, so in this situation, there is a transfer of energy from the piezo injector toward the main source, the voltage VD that we had at the voltage side, voltage port of our half bridge. Okay, so there is a say transfer of power from the right to the left. In that specific situation, the operating mode of the half bridge is similar to that of a boost DC-DC converter, okay, in which the input side now is what traditionally was the output, okay? So VP for me is the input of this boost converter, and voltage VD is the output of this boost converter. Remember that in this specific range, which is called T-fall, that lasts for 100 microseconds, the duty cycle of my half bridge is reducing from 0.8 to 0. Okay, and so it has this specific equation, okay, that we previously derived. The transistor TA plus is always left open, is off. Okay, so the only two devices that conducts the current are the transistor TA minus and the diode DA plus. Okay, so this one and this transistor here. We have a boost, so we have the classical function that relates the output and the input of a boost converter, which is 1 over 1 minus the duty cycle of the transistor. And this is the dA minus. Okay, dA minus is 1 minus dA. Okay, dA is the duty cycle by definition for the transistor TA plus, for the I side transistor. This equation says that for dA minus, which is 1, V out is infinite, but as we discussed last time, this is not possible. Okay, there is no energy transfer when the duty cycle dA minus is 1, because in that situation the transistor TA minus is always closed, and so there is no direct connection between the input and the output. So it is basically something that is just a mathematical description, but if you see what happens in practical circuits, the curve that relates the output with the input versus the duty cycle dA minus is something like this. So when the duty cycle is 1, the ratio goes to 0. Okay. The same horizontal axis can be also discussed in terms of dA, which is 1 minus dA minus, if you want. And so this is my the point that we had last time. Okay. So what happens that in the discharging phase, in which you have the boost operating mode, basically you are recovering the energy. Okay, so you are transferring energy from the output, from the piezo actuator, toward the input. In that situation, you are, say, recovering the energy that you previously provided to the piezo injector in order to make it, deformed in order to open the injectors. But according to this discussion, we can say that you cannot have the boost for the entire duration of the duty cycle from 0 to 1. Okay, so this is only possible for a specific maximum value. Okay, for example, you can see that the boost action is something that can be, say, true from duty cycle 0 to, I don't know, this maximum value. Let me put here dA minus maximum. Okay, from this point on, then the ratio is no more, say, to have V out higher than V in, so we are no more in boost operating mode. It is reducing. Okay, and so this is no more a boost operating mode. Let's suppose, for our purpose, and also this is just for simplifying a little bit computation, that the maximum duty cycle dA minus for which you have, let's say, the boost operating mode, so you have the maximum of this curve, is at the value of 0.76. Repeat myself, this is just for simplifying computation, but I have to say that this is a value that is, let's say, typically in practical application, this is true. This maximum, depending also on the parasitics that you can have, it is in between 0.7 to 0.85, somewhere in between these values. Okay, so 0.76 is something that can be true. Okay, in terms of the duty cycle dA, which is 1 minus dA minus, this is 0.24. Remember that dA is ranging in this phase from 0.8 to 0. So it is ranging from, let's say, 0.8 to 0. So now I'm saying that my duty cycle, in which we have effectively a boost action, so a recovery energy phase, lasts for duty cycle dA, which ranges from 0.8 down to 0.24. Okay, so what about the output voltage? So what is this voltage here for duty cycle dA minus 0.76? But you have to, say, consider this expression. Okay, and using this expression, you can see that V out boost is V in boost over dA. And so from this expression, you can see that V out boost is the output voltage, so this is VD. V input boost is VP, the output voltage across the capacitor. And so from this, we can see that VP is duty cycle multiplied VD, 0.24 multiplied for 250 volt was our VD, 60 volt. Okay, so basically it happens that in this phase the voltage VP from 200 volt goes down, eventually reaching 0, but it happens that when it reaches 60 volt, from this value on, we have no more boost operating mode. Okay, the boost operating mode is only effective in this interval here. Okay, when the voltage is higher than 60 volt, which is the time interval, this time interval here, in which the boost is effective. Let me call this T star. Okay, but in order to find out this star, we have to consider this expression, this one. Okay, and from that expression you can see that T star is simply T fall minus Vp over Vp maximum multiplied T fall. So it is 100 microsecond, 60 volt over 200 volt multiplied 100 microsecond. And this is 70 microsecond. So after 70 microsecond here, 70 microsecond, this interval, you have no more boost action. So there are, let's say, remaining 30 microsecond. The difference here is 30 microsecond, in which you have no possibility to recover the energy from the piezo injectors to the VD power supply. This star happens in a situation in which the output current basically is negative 10 amp. Okay. So, summarizing all the discussion, it can be useful to recover the energy. Okay, because you spend energy for elongating your piezo injectors, making the injectors open to inject the fuel into the combustion chamber. Then in another phase, you have to, say, compress your device in order to close your injectors. In this phase, you are recovering energy, so you are acquiring energy, and this can be, say, something good to recover to the energy previously spent. But this is not possible for the entire duration of default. The boost operating mode is only effective for 70 microsecond of the total 100 microsecond. For the remaining 30 microsecond, there is no possibility to recover the energy because the boost is not is no more a boost. Okay, you are in this region here in which you are not, let's say, providing energy. So what happens? That there is a phase in which you are recovering energy, exploiting the boost operating mode, and then there are a small fraction, which is basically not so small, okay, the 30% of the default, in which this energy cannot be recovered. And then you have to dissipate this energy. Okay, the energy cannot go through the supply. Okay, and then you have to dissipate somewhere. So the problem is that what happens, and in which way I can dissipate this energy in my circuits. So the problem is to understand which way you can dissipate the energy for, say, t higher than 70 microsecond during t fall. Okay. We can use different methods. Okay. Let's start with the first one. Let's call me A. You can dissipate the energy, cannot be no more recovered, by using resistor. Okay, so what happens? Let me just redraw my circuit. Let me put here switches in place of transistor just to, say, simplify my drawing. The two freewheeling diodes here. Voltage, constant VT. Input capacitor. TA plus, TA minus. L and CP. Let me put here a circuit, which is this one. R, this is a switch S. Okay, so this circuit, okay, which is made by the series of a resistor and a power MOSFET, is always left open, okay, because it's not used for example, during the back operating mode where you're providing energy, it will open, okay, and also during the boost operating mode from 0 to 70 microsecond during default, it will be open. When it will become active? Only after 70 microseconds. So only after the boost operating mode is the more effective. In that specific situation, both the transistor Ta plus, which is already left open, but also Ta minus are left open. Okay, so the two transistors Ta plus and Ta minus are open, and then the switch S becomes active, so it is closed. For T higher than 70 microsecond, let me call that Ta plus and Ta minus are off, so both left open. So the half bridge is disconnected. Okay, there is no let's say connection between the voltage VD and the output side. Okay, and at the same time the switch S is on. Otherwise, S is off. So what happened when the transistor it's closed? So what happened when the voltage between the gate and the source is higher than the threshold? But the circuit becomes like this one. Now I am answering your question. Okay, let me just finish. Okay, I have a question from Antonio Moles. Can you repeat how we derive T-fall from 7? T-fall from, how can we derive? No, it's the opposite. 70 microsecond from T-fall, maybe. T-fall is something that we derived at the beginning, okay? Because if you remember, we have a slope that has 2 volt microsecond. So we have 200 volt, so that the falling phase as the rising phase lasts for 100 microseconds. Okay, so we can call this T rise for the energizing phase, or T fall for the discharging phase. So this comes from the maximum 2 volt microsecond rate for the voltage. Okay, so from this expression, this one that describes the variation of the duty cycle during T fall, and this is the expression. For example, when T is equal to T fall, the duty cycle is 0 here. And when T is 0, then we have the duty cycle is 0.8. So this equation describes the variation of the duty cycle during T fall. Okay, we can find that the time interval in which you have an effective boost is 70 microseconds, because we know that the duty cycle is 0.24. So we have this value here. Vp max is 200 volt, Vd is 250, and so the T fall is 100 microseconds, so the only unknown is T. So we derived T from that expression. Exactly this equation here basically comes from the previous expression. Okay, where Vp is given by this quantity. Okay, thank you for the question. So basically, when the switch is active, so after 70 microseconds, when the boost is no more working, the circuit that is remaining is just this circuit here. And the circuits make possible for the energy inside the capacitor to be dissipated by the resistor R. Of course, the resistor R should be less than the voltage Vp over the current Ip. The voltage Vp for which we can start this, we can make this circuit working, is the 60 volt. Okay, 60 volt, and then Ip is 10 amp. Remember that in this phase, okay, we have 60 volt here when the boost stops to be effective, and in this situation the current is 10 amp, negative 10 amp. Okay. Basically the resistance is to be computed in this way. So it is, let me say, less than 6 ohm. This circuit here makes possible to dissipate the energy with an exponential, say, variation. Okay, this is a circuit which has a time constant. The time constant is tau, which is R multiplied Cp. Let me consider R exactly 6 ohm, so 6 multiplied 5 microfarad, which is the value of Cp, is 30 microsecond. This is the time constant. So let me put here the plot for the voltage Vp across the capacitor. We have Vp max, which is 200 volt. Then we start at this point the discharging phase. This discharging phase is, say, operated by the boost operative mode up to the voltage 60 volt. This phase is 70 microsecond. From this point on, we have our resistor operating. The expression for the voltage Vp is 60 volt multiplied E minus T over tau for the circuit. And so from this point on, we have this exponential variation, okay, which is something like this. So here we have these circuits. In this phase, we have the boost. So let me just consider, remember that our T fall is 100 microsecond. So what is the voltage that you have across the capacitor Cp after the standard T fall we we used so far? Vp for T equal to, say, 30 microsecond is 60 multiplied E minus 30 microsecond over 30 microsecond, which is the time constant. So this is 60 E minus 1, this is 22 volt. So here we have 22 volt. So in our ideal situation, after the fall 100 microsecond, we should have 0, okay? 0 after 100 microsecond. Using this circuit, using a resistor to dissipate the energy that we cannot no more recover, we have 22 volt. Where this voltage across the, so that means that my injector is not fully closed, okay? There is a remaining elongation that makes it impossible to close this injector. When this injector is fully closed, so when the injector, the voltage across the Cp capacitor is null, but we have to wait for several time constant. Let me put, I don't know, from 4 to 7 time constant. 7 time constants means 7 multiplied 30 microseconds, so 210 microseconds. So it means that from this point I have to wait for, say, 7 tau in order to have effectively the voltage across our Cp to be null, so we have the injector fully closed. So this, if you want, this is a drawback, okay? Because I want to respect very precisely the timing constraints that my, say, injection computers give to the all the injectors systems. But in this case, I have to wait for the discharging phase, an exponential phase that is a little bit longer. Then there is another drawback in doing this kind of dissipation. Let me consider, for example, the power which is dissipated by this resistor. Okay? In order to understand which is the power dissipated by the resistor, let's start by some computation by the energy involved in this circuit, which is the energy which is stored into the capacitor CPE, the piezo injector, at the beginning of the discharging phase. The beginning of the discharging phase is here, when the voltage Vp is 200 volt. Okay, so the energy which is accumulated, stored, is 1F Cp multiplied Vp maximum square. So it is 1F 5 microfarad multiplied 200 volt square, 100 millijoule. This is the energy stored into Cp at the beginning of the discharging phase. Which is the energy which is dissipated by the resistor. Let me call this energy dissipated. The energy is, say, the energy that we have to dissipate is 1F Cp Vp at the beginning of the phase in which the resistor R is working, so it's 60 volt, minus the energy at the end, so it's 0. So it's 1F 5 microfarad multiplied 60 square. It is 9 millijoule. This is the energy dissipated by R. So if you want here, you can find also the energy which is recovered. Energy recovered by the boost operating mode, it will be the difference. Okay, this is the Cp minus the energy dissipated. So it is 91 millijoule. Okay, recovered thanks to boost operation. Okay, but anyway, for computing the power dissipated by the resistance R we just added, we have to consider the dissipated energy, which is 9 millijoule here. And so we can consider that the average power across the resistor is the energy dissipated we are computing the average power over T cycle. Okay, so this power that I computed here is just dissipated for one pulse. Okay, because this waveform here is the waveform for just one Vp pulse. Remember that we have 10 of these pulses, okay, during T cycle. So we have to multiply this energy for, say, the number of, let me call this Ti, because Ti is the duration of these pulses, so Ti pulses over T cycle divided by T cycle. So it is 9 millijoule. The number of Ti pulses is just 10. We have 10 pulses, and then T cycle, which is 20 milliseconds. So it's 4.5 watts. So basically, this is, say, is not exaggerated, but it's somewhat larger. It means that this resistor that we added here, it's bulky, it's heavy, it's say require it has a certain dimension, okay, because you have to wait to dissipate 5 watts, almost 5 watts, okay, and basically this solution does not permit to have after 100 microseconds the rest position of my injectors. So we have to wait some time constant for this voltage across the injectors to be completely zero. Okay, so sometimes you can find in this kind of application in which you cannot recover the energy to dissipate the resistor. Pay attention, that can be you can have some drawback in terms of power dissipation, in terms of timing of your system. So let me consider another different solution for doing the same job. Okay, and let me call this as B solution. And this solution is based on the use of a Miller integrator. Let me draw again my half bridge. Here we have the Piezo injector. Okay, the same reasoning. Okay, when we are in the boost operating mode, the transistor TA plus is off, and we are switching the transistor TA minus. Okay, then there is a certain point after 70 microseconds from the beginning of our discharging phase in which the boost is no more effective in recovering energy. So I have to put all the transistors to be, say, off, and I have to find out another means to dissipate the energy that can be no more recovered. So now the circuit is a Miller integrator. So let me put here an operation amplifier with a capacitor in its feedback. So RE, then we have a voltage, VE here, and this is CI, RI, CI, VE. And this plus is to, say, the reference. I put this circuit here. This is a simple integrator. Employ a, say, operation amplifier. Let me put in the standard well-known form. Okay, this one. The voltage here at the output is, say, the voltage across the capacitor. Okay. So this is the Miller integrator. Let me just derive a little bit the equation. Okay, first of all, I have to say that the voltage VE, that is the voltage supply in the Miller integrator, is say equal to a constant voltage VE when the voltage VP is less than 60 volt. Okay, so it is operate, otherwise it would be 0. So basically the Miller integrator is only active when the boost is no more effective. So when the voltage VP is less than 60 volts. So after 70 microseconds from the beginning of the discharging phase. The current, let me put this current flowing here as II. So II is what is VE, constant voltage, versus RI. Okay, remember that this node here has the same potential of the, say, non-inverting node, so this is 0 volt here. This current II is flowing where? But it cannot flow inside the operation amplifier, okay, and so it flows interiorly here. So it becomes the current ICI. So this is also ICI, and ICI is a current flowing through a capacitor, so it is the VCI over the T. And so the voltage VCI is this one, but since this node is, say, at the potential of the reference, okay, and this node is connected to VP, we can say that VCI is, say, negative VP. So this is CI, the VP over the T. From this expression, I can say, derive VP, the output voltage. So VP is negative 1 over RICI, the integral of VE dt, plus the initial voltage across the capacitor. So we can see that this VP T star minus VE, which is a constant, so we can say put outside the integrator RICI multiply T. Okay, this is, let's say, the voltage at the beginning of this action is exactly 60 volt. Okay, so the voltage at the beginning of the dissipation phase. So let me plot now the voltage VP across the capacitor. We have the constant phase, holding phase, whatever here. Then we have to start the discharging phase. This is a boost discharging phase down to 60 volt from 200 volt here. Boost phase now here, and this is 70 microsecond. The boost action is no more effective. Then the voltage, the integrator, the Miller integrator now is operated. Both the switch are left open here. And then we have this expression, but this has a linear variation in terms of the voltage VP. For example, if I put negative VE over RICI to be exactly negative 2 volt microsecond, which is this slope here, then we have that my slope is exactly this one. And so it means that I have in 100 microsecond the voltage VP across the capacitor, which is exactly null. So I have effectively the behavior I'm expecting for my timing interval. Okay, so I have to use this expression to derive, to design the voltage VE, the resistor RI, and the capacitor CI. Okay. Let me just stress a little bit the drawback of this solution. This solution is good for, let's say, the idea. So to use an integrator to do the job. Okay. Basically, the implementation is something that cannot be directly implemented. Okay, but the idea is good. So we can exploit later the idea, but then we can get rid of this implementation. Why this implementation is not, let's say, so practically implemented? Basically, the voltage VP that I have here at the beginning of my action is 60 volt. Okay, so my integrator have to work from an output voltage which is 60 volt. So what does it mean? It means that I have to supply my integrator here with a voltage source, a supply that will be, let's say, 60 volt. So it's something that is not, say, easy to have available in circuit. For example, you have to generate 60 volts starting from another, say, voltage that you have available in your vehicle. And the other characteristic that the current IP that I have during this phase is negative 10 amp. So it's a current flowing here having a value of 10 amp. So what does it mean? It means that the current that you have at the output of your operational amplifier is the sum, basically is the sum of these two currents here. The current ICI that previously, say, discussed, that goes here, and then 10 amp here. So the current here is higher than 10 amp. So this operational amplifier basically is a very large power operational amplifier. So it is a power circuit by itself. So basically this solution is not easy to apply practically to your circuits. Okay, so as I said before, the idea is good. The integrator is good for having a linear variation during the dissipation phase. Okay, make possible to, say, respect the 100 default timing, but it's not good for implementation. So let me move to the third solution, which can be, say, something more applicable, which is the Miller integrator, but with MOSFET. Not operational amplifier, but using MOSFET. So in that case, let me just again, for the third time, drawing our half bridge. L, here we have the CP capacitor. Now I am adding a circuit which is always off, is not present during nominal operation. It is only working during the time interval from 70 microseconds to 100 microseconds during the discharging phase, in which the boost is more effective, like all other circuits A and B previously described. Okay, the circuit is this one. I have a MOSFET. And I have a resistor CI, RI, and a capacitor CI. Okay, so as usual, TA plus and TA minus off when VP is less than 60 volts, so after 70 microsecond, and VE is a voltage VE in the same time interval. Otherwise, VE is simply off, so the transistor is off. Okay, so the transistor, let me put is S, is off. So what happens during the time interval in which you have this circuit, the red one, activated? Then basically we have just this circuit. We have just this circuit here, okay, in which you have the voltage VP, the current IP here. The current is negative, so the current effectively positive direction is this one. Okay, so this circuit works if we have an initial assumption, and the initial assumption is that the current ID flowing through the MOSFET basically is the current IP max, so it is say 10 amp flowing into the piezo injector. So what does it mean? That suppose that here we have a current which is called IF, the current flowing to the capacitor CI between the gate and the drain. It means that the current IF is be negligible with respect to the current flowing in the circuit. Let me call this current here IP, sorry. ID is IP. It's already there. Okay, this one. Okay, this is IP. IP is the current flowing to the piezo injector and is similar to ID. Since ID at this node is IF plus IP, basically this means that the current IF is well less than IP. Okay, so in order to get this approximation, when you operate these circuits in which you have this capacitor across the gate and the source, you are effectively exploiting the Miller effect. Okay, this discussion was already made to students in mechatronics during the section of lectures devoted to the devices. Okay, maybe they can remember that when you are exploiting the Miller effect, basically this circuit, which is an amplificator, okay, if you regard this amplificator from the input ports or from the gate source, is like a circuit in which you have an input capacitor CI, which is multiplied by a huge factor, which is basically the amplification of this circuit. Okay, so it's like to have a very large capacitor across the gate source. Okay, students in electronics should know this effect. I think that is something that should be well understood. Okay, so that situation exploit the Miller effect, and exploiting the Miller effect, it means that basically the voltage across the gate and the source is basically a constant voltage due to this effect. Okay, so due to the Miller effect, VGS basically is a constant voltage. Let me put this as VGS IP. Constant. Because we have a large capacitor that holds the voltage across the gate source port to be more or less constant. Let me just redraw the circuits here to avoid go back and forth slide. Okay, this is the circuit I'm talking to. This current IP is 10 amp. The current ID basically is IP. The voltage here is constant to a value that I define as VGS IP. So the VGS, which is related to the current ID, which is basically IP. Let me consider the current IF, which is flowing here. The current IF is CI multiplied the voltage across this capacitor. The voltage across this capacitor is VGS IP minus VP. Over the T. Of course, in this derivative, this quantity, which is constant, does not play any role. So this is negative CI the VP over the T. This is IF. And which is the current expression of the current IP. IP is the current flowing through CP, so it is negative CP the VP over the T. So we have these two quantity. ID, as I said before, here is a summation between the two. Okay, and so I can see that ID is negative CI plus CP the VP over the T. So basically my previous assumption to consider the current ID, which is the same of the current IP flowing through the piezo injector, by looking at this expression is true only if CI is well less than CP. For this expression assumption that I had before, so this assumption here, okay, effectively is true. Okay, so if you have this expression here and then you have this quantity, let me put another equation, which is the basic design equation. That is this one. The current flowing through these resistors Ri basically is the same current flowing through IF here. Because this constant voltage here avoid any current flow through the internal capacitance, the CGS of the MOSFET, okay? Remember that here you have a parasitic capacitance, which is called CGS, but this CGS is subjected to a constant voltage here, so no current can flow here. Basically, in that situation, the MOSFET is not absorbing any gate current. And so all the current flowing here is the current IF. But I can compute this current here, because this current here is VE minus VGS IP over RI. So VE minus VGS IP over Ri, which is IF, is negative CI the VP over the T. From this equation, we can derive another one. We can extract the ratio dVP over dt, which is negative VE minus VGS IP over Ri Ci. And this is the basic design equation. We have to design this slope to be equal to the required slope, which is 2 volt microsecond. And so in that situation, we can say have our mill integrator. This is the same expression that we had for the the amplifier, okay? But we have no need for supplying. And then the MOSFET can be, say, a MOSFET that can be get from commercial, say, available market, just having a current flowing through it, which is 10 amp, which is something that we can get without any problem. For example, let me just put numbers. Consider that my VE is 12 volt, which is basically a standard voltage for turn on a MOSFET, a power MOSFET. Supposing that VGS IP, which is the voltage VGS, basically, at drain current of 10 amp, is 5 volt. You can find this quantity on the data sheet. We need that CI well less than CP. CP is 5 microfarad. So we can use, for example, CI 15 nanofarad. And then we can use this expression to derive Ri. Ri is VE minus VGS IP divided CI the VP over the T. So Ri is 12 volt minus 5 volt divided 15 nanofarad multiplied 2 volt microsecond. You can see that this is 233.3 ohm. Of course, the resistor should be higher than this value, and so you can have a normal standard value of 270 ohm. The MOSFET should have a current flowing to the drain, which is, let's say, a bit higher than 10 amp, a voltage VDS, which is higher than what? Remember that this transistor is always off. So when the transistor is off, the voltage appearing across the drain, the source terminal, should be always less than the breakdown voltage of the MOSFET, and which is the maximum voltage that you can see across this transistor is the maximum voltage VP max, which is 200 volt. Okay, so here you have that the maximum VDS should be higher than 200 volt. So the breakdown voltage of this MOSFET should be, I don't know, 250, maybe is enough. For the resistor Ri, the value should be, I don't know, 270 ohm, and the power is Ri multiplied what? Which is the current flowing to the resistance Ri, is the current IF. And this is 270 multiplied the current IF. The current IF is negative CI dVp over dt. So it's negative 15 nanofarad multiplied 2 volt microsecond. So it is 30 milliamp. So 30 milliamp square value. And this is 210 milliwatt. So quarter of watt is enough for this resistor. Okay, no problem of dissipation. Another constraint that we have here is that the capacitor Ci should be less than the capacitor Cp, okay, in order to have the current flowing to the drain to be constant. But remember that any MOSFET, any real MOSFET here, across the drain resistors, there's another parasitic capacitance, which is the CDS capacitance, okay? And this capacitance, which is CDS, between the drain and the source, typically in datasheet is called also C CRSS. Okay, so in datasheet, this is the name given to the CDS capacitance. Of course, CI should be larger than CRSS, okay, in order to dictate the operation of the circuits. Otherwise, it will be CRSS that, say, dominates, and so is not, say, something that I can design. So to look at the datasheet, which is the value of this capacitance, let's put CI, which is quite larger than that, and quite lower than CP. Okay, another consideration that we have to make about this circuit here is about the MOSFET. The MOSFET has some static consideration, the current higher than 10 amp, the voltage higher than 200 volt. But another consideration that we have to make is about the dynamic characteristic of the MOSFET, because the MOSFET has to be turned on in a time interval that should be much lower than 30 microseconds. Remember that my action, okay, here, okay, I have to turn on my MOSFET exactly here, when the voltage across the capacitor CP is lower than 60 volts. So when the boost action is the more effective. So I need a MOSFET that is able to become on, so to be effectively a closed switch. So in that situation, to be operated as an amplifier in a time interval which is well less than 30 microseconds. If we buy a MOSFET that is very slow, and so it, say, turn on action is a non-negligible fraction of 30 microseconds, all the operation is not working. So we have to buy a circuit at the MOSFET that is able to turn off in well less than 30 microseconds. So here we have to add that MOSFET has to be turned on with a time interval T on which is well less than 30 microseconds. For example, let's have a few percent, say 3% of 30 microseconds. That means that T on should be, for example, I don't know, 900 nanoseconds. Okay, the quantity, the interval should be expressed in in a few percent of the total 30 microsecond interval. Okay, so for example, how can you drive this MOSFET? Electronic students should remember that they have to look for the VGS over QG curve, which is the gate charge curve. Students in mechatronics, they have this curve explained during the lecture. Okay, this curve is something like this, providing you the quantity of the charge that I have to provide to the gate source port of the MOSFET in order to reach specific voltage VGS. The voltage VGS I have to get is the voltage applied from the external side, the voltage, let's say, VE, which is 12 volt. And so look at the charge that I have here. This is the charge that I have to provide, QG total. This graph is described in the datasheet, the manufacturers of the MOSFET. Suppose, so for example, let's suppose that for that transistor I'm considering for my circuit, QG total is, I don't know, 30 nanocoulomb. So here I can have 30 nanocoulomb. So which is the current I have to provide by my external driver for the MOSFET is QG total divided the time interval T on. So 30 nanocoulomb after over 900 nanosecond, previously computed as a 3%, and this is 33 milliamp. Okay, so this is something that can be easily obtained by small driver. Okay, so I'm talking here about the circuits that you have to put here. Okay, there is no voltage VE. There is a driver circuit that has the capability to provide the current through the gate, which is enough to make the transistor turn it on in that specific time interval. Okay, 33 milliamp is not so huge, so you can find easily as a commercially available driver. Okay, during the turn on and off, the gate current is not null. The current through the MOSFET is just null for static operation, but during, let's say, the turn on and off, you have to charge and discharge internal parasitic capacity, and this is the need for this driver behavior. Okay, have you questions about this, say, computation, this, say, discussion? Problems? Yes. Federico Desario asks, can you repeat how we choose Tion? Okay, Tion is basically making a transistor to conducting or made a transistor to be interdicted is an operation which lasts for a certain amount of time. It's not instantaneous. Okay, you put a command in your, say, at the control port of your transistor, in this case the gate source port of your MOSFET, and at the time instant which you put this command, for example, to be turn on your transistor, at the time in which the transistor effectively turn on is not zero. Okay, this time interval is called T on for the turn on, or T off for when you are turning off your transistor. Okay, what happens when, in my application here, the turn on of the MOSFET is, say, where is the plot here? Is a large fraction of the overall 30 microsecond. Here, I have to put the transistor here to be turned on. Okay, the transistor is always off. When the boost action is no more effective, I have to put the transistor, the MOSFET at the switch to be on. Okay, so this is the time instant at which you put the command for the transistor to be on. But then what happens that if the transistor is low, maybe the transistor will be on at this point. So there is a large fraction of the total at 30 microseconds which the transistor is again off. And so the energy that I have to, say, some way dissipated is not possible to dissipate. So I need a transistor that can be close fast enough to, say, cover all the 30 microsecond interval. As a, say, matter of fact, I can choose for a MOSFET having a turn-on time interval, which is a small fraction of 30 microseconds. I decide for a few percent of 30 microseconds. For example, in my decision here, your decision can be different. Is to have, let's say, 3% of 30 microseconds. So it means that after 900 nanoseconds, my transistor is effectively conducting devices. Okay, for me is enough. You can choose 5%, 2%, whatever. If you choose for a transistor which is very fast, it means that you have to provide enough charge during T-on for charging the parasitic capacitance. And so this is require a very huge current flowing to the gate. And this is the reason why I have to compute the current flowing to the gate for T-on interval I decided. In this case, not, it's so huge, okay? If here you have, for example, I don't know, 25 amp, okay, this is not possible. You have to, say, relax a little bit this time interval, this T-on, but this is not the case. One to 3% of resonant time, yes, 1 to 5%. A few percent means, let's say, I don't know, 5% is enough, okay? 5%, 2%. Okay. What we have still to, what we remain to design? We design L. We design L. We design the dissipation circuit. We design the voltage VD. We have to design the capacitor CD. So let me put here, let me start basically computation for designing CD. Okay, so design of CD. We already derived some important expression and quantities for the energy stored into CP. For example, we define the energy stored into the capacitor CP for getting, let's say, a voltage excursion across CP from 0 to 200 volt. Okay, this is 1F CP VP square maximum. Remember, we computed these are 100 millijoule. So this is the energy stored into CP that make possible to have a variation of the voltage across CP from 0 to 200 volt. Okay, this is the energy stored into the capacitor, for example, at the beginning of the discharging phase, previously computed. Then we have also computed the energy which is dissipated due to the impossibility to recover it. Okay, and this is 9 millijoule. This is computed as 1F CP VP square, where VP is 60 volt, the beginning of the, say, non-boost phase, let me say. All these quantities are computed referring to the CP, the capacitor CP. So these energy are referred to the CP side of my converter. Let me again to plot here the half bridge and then the load. We have here CD. So we basically computed this energy by referring to these CP values. So they are energy that are relative to the, let's say, the load side. They are relative to this side here, okay, because they be computed by looking at the energy stored into CP, okay, or the energy that is stored into CP that you have to dissipate. Basically, and so we have also the energy which is recovered, which is the difference between the two. Remember, 91 millijoule. These are also referred to CP. Now, just to reflect all these quantities from the load side to the input side. In order to do that, we have to know, or better, at this stage of our design, just to assume, to have some assumption on the overall efficiency of my system. Okay, so let's suppose that my system has an overall efficiency of 0.8. Of course, this is just an hypothesis. At the end of my design, I can recheck my computation to see if this is true or not. Maybe I can have some simulations, and so I can say tune my design in order to have a better hypothesis based on simulation or, say, computations. Okay, but at this stage we can say that, okay, suppose that my efficiency is 0.8. What is the efficiency in the system? The efficiency is the power that I have available at the output with respect to the power that I, say, have at the input of my circuits. Okay, in terms of energy, this is the energy that I provided to CP which is the output of my circuit, Cp is on the load side, with respect to the energy that I have at the input. Okay, so Cp is the energy provided to Cp to get a voltage swing from 0 to 200 volt. Okay, and this is the energy that is required to the input of my circuit for the same swing. So, for example, giving 0.8 as an efficiency, I can see that the energy at the input is Cp over eta. So it is 100 millijoule over 0.8. So 125 millijoule. So if, let's say, 100 millijoule is the energy that is stored, must be provided to Cp for having a voltage rise across it from 0 to 200 millivolt, these quantities evaluated at the input side, so the energy that I have to provide from the input side to get this voltage excursion at the load side is a little bit higher, okay, due to the efficiency, which is not 1, is say less than 1. So you have to provide 125 millijoule from the input side to the load in order to get across the capacitor an excursion of the voltage from 0 to 200 volt. Okay. The same happens for the energy which is recovered, but the energy which is recovered is energy which has a different path, because in that situation the power flow goes in this direction for recovering energy. So the input and the output side are reversed. What is previously was the input now is the output, and vice versa. So it means that in terms of recovering, for energy recover, eta is the energy which is recovered, let's say, at the output, which is now, let's say, the CD side, with respect to the energy which is recovered at the Cp side. Okay, this is something that we already have as a computation, is 91 millijoule. Okay, now the input and the output are, say, reversed. So from here we can say that the energy recovered, as we can see from the input, so at the CD side, is eta multiplied 91 millijoule, and this 72.8 millijoule. So the energy which is stored in the capacitor Cp that can be recovered is 91 millijoule, and this corresponds, due to the efficiency of the system, to 72.8 millijoule at the input side. So basically, let me just put this in a graphical description. We have that the voltage Vp, and then from this graph we can continue tomorrow. I have the voltage Vp as this behavior, okay, for a single pulse. 200 volt, which is Vp max here. Remember, this is 100 microsecond. Here we have a 70 microsecond, and here I have the recovering action. And so what happens to the current? The current, to the energy. The energy in this section, which is a section in which I am providing energy from the input to the output, I have 125 millijoule to be provided. And here I have something which is recovered, which is negative 72.8 millijoule. Okay. Of course, during this part here, the energy is dissipated, so there is no input energy. Let me put here energy at the input side, because the switch TA plus and TA minus are left open, so there is no connection between the input and the output side. Okay. So this happens. So this energy is provided from the input to the load in order to have this voltage excursion. And this voltage here, this energy here, is the energy that you can see that is recovered to the input side due to the boost action that is from 200 volt to 60 volt here. Okay, so let's finish here, then can continue tomorrow, exactly started from this design for the capacitor CD. If you have questions, I can answer your questions. Otherwise, for students that will come in the lab, we can see each other this afternoon. Otherwise, for all other students, tomorrow at 11:30. Okay, it seems to me that there are no questions, so I'd like to thank you, all of you. See you tomorrow. Bye.